Hello, chemists. Jolly here again. Let's finish out those radicals. So we're going to talk about their basic characteristics and some real life ones. Back to the handout. All right, just what are some characteristics of your polymers? Well, number one, they can be made of the same monomer over and over and over, or they could have alternating or multiple compounds in them. And I'm just going to be really generic. So a homopolymer would just be all of the same one, where a co can be two opposite. However, they can be alternating or random. So the one I drew looks like it's going to be alternating. How about, it's kind of hard to do random. So this is alternating. And here's my example of something. Okay, or there's random. So basically how you put the pieces together. Now, if they get large enough, they become crystalline. So most of the polymers we're familiar with are some kind of a solid. But what is the difference between the solids? Well, crystalline, remember, has a very nice ordered structure, where amorphous does not have an ordered structure. So my wonderful little picture of crystalline for polymers. Okay, it's going sideways, but there's crystalline. Oh, here's amorphous. All over the place. Okay, so for those, how are you going to determine it? That is beyond the scope of what we need to talk about here, and sometimes it's just really hard to. But I guess you could have a combination between them. You could have a portion that is crystalline, and then there's a little wig out, and then some crystalline. Those are called semi-crystalline. But it is very important how they pack, because it will help you determine how they're useful. All right. So let's talk about those backbones. Now, I know you have not seen the proteins with me. That's the end, but this is really funny because this is very, very similar to how we're going to talk about proteins in the future. But linear, okay, it packs really tight. Then we could have branched. Okay, we saw those examples in the last video between amylose and amylopectin. We could have cross-linked where they're actually linking to somebody else. And then we can have them all in a networked kind of an idea. So linear, we'll kind of put like that. Where branched, okay, those are harder to link together. Okay, so they don't pack as tightly. Cross-linked, literally has a nice little attachment right there. And then networked are more in these ordered structures. And again, it depends on what you want the polymer to do, whether, each packing is useful or not. And one that you are familiar with is HDPE, high density polyethylene. It's branched, so it's very flexible. And LDPE is I'll just say linear, not branched. And so it packs much, much tighter. So high density polyethylene and low density polyethylene. And I haven't really researched those, but they blow air into the polymerization final process to kind of keep them from packing too tightly, I believe is how they make either the high density or, of course, the branching. But there's a few ways that you can get a little flexibility into your polymers. Well, what is another characteristic? Okay, those R groups. What do you want attached to your polymer? Ah, well, if you don't want it to pack very tight, okay, there's only two answers in organic chemistry, sterics and electronics. So if you don't want it packing tightly, use something sterically hindered. If size, and intermolecular attractions. Okay, some functional groups that matters. They can affect the strength of attractions between the neighboring, and this is so like proteins, but they can form hydrophobic attractions. Hydrophobic. That's basically London forces. Remember, like dissolves like, so nonpolar portions will gravitate towards nonpolar. You can have salt attractions, which is just an ionic attraction. You can have hydrogen bonds. And they actually can be linked together in covalent bonds as well. Okay, so the side groups will determine their size, but it can also determine how it interacts with its neighbors. Now, how are you going to control chain growth? Okay, that's a tricky business. So you can limit starting material, you can, use colder conditions, but shorter chains can more easily slide past each other, and longer chains tend to get tangled. And just one fun note in the laboratory, if you use a low concentration in a radical polymerization, if you use a low concentration, you tend to get larger or longer chains. So think of it this way. If you put the fish that was starving into a bowl of two pieces of food, well, it would go after those two pieces. But if you put it into a whole bunch, do you see it could take a nip off each side? So if you keep it a low concentration, that first radical formed will find the next one, and then it will find the next one, and you have a chance of making a longer chain. Whereas if it's a high concentration and you start a radical, well, those radicals can just start going all over the place. Now they're reactive anyway, but it's just kind of an odd thing. All right, now the tasticity. How the side groups are arranged. This is an interesting one to draw, but isotactic is they're all on the same side. So again, just kind of a jolly drawing. When you make your polymer, they're all on the same side. Or syn means, okay, this is not what we normally think of syn. Okay, alternate positions. So please don't confuse that with the syn that we've used in the past. And then the atactic. That's just random. But that also could be important depending on what you want your polymer to do. All right, the next questions are not to be intensive. I just wanted to give you some visuals of what these could be, and you try and put the terminology with it. So, homopolymer versus copolymer, alternating versus random. Can you figure out, is there enough information to tell me, its backbone? And then if you can tell me about its attachments. Again, not every answer can go to every problem. Let's do this first one together. All right, this looks like a repeating pattern of the same monomer. Okay, so it's a excuse me, a homopolymer. Is it alternating or random? This, oh, so homopolymers, they don't alternate or random because there's only one. So I can't answer that one. And it looks pretty linear. Okay, so there's no attachments between them. It's not really branched. And the way I've drawn it here, they're on the same side. So unless for some reason my brain got those words wrong, that's not the sin that we've always talked about. And that's how I've been remember it. It's not sin, it is iso. And remember, iso generically means symmetrical. All right. And then we can do that for all of these. Can you pick out the starting material? Just take a look at them just to get familiar with some of the terminology. And then I actually found you some molecules of real polymers. This one happens to be vulcanized rubber. Look at this. So if you've had any biochemistry, that's a disulfide bridge. That's the reason that rubber really stinks, at least it does to me. Okay, that is vulcanized rubber. Over here, okay, it's kind of showing these little hydrogen bonding attractions. Woo! There's those amylose versus amylopectin. Now, there's a very common one that uses AIBN in nature, and I wanted a picture of, ooh, look at the symmetry in those branching. So there's not a lot of here to do other than pick out, those terms again. And there's a picture of starch, glycogen, and cellulose. Oh, is that DNA? Why, it certainly is. Did you know DNA is a polymer? Why, yes, yes, it is. Okay, so again, try and put some terminology with those, but I wanted you to see some real life examples of polymers. And last but not least, where are you going to see these polymers in real life reactions? Now, of course, those ones that I showed you just above, but let's talk about the atmosphere first. Hey, lots of energy up in the atmosphere. And remember, energy from light can get radical reactions going. So it does depend on the chemical compounds present. It does depend on the physical conditions. Is it daytime? Is it nighttime? Is it really humid? Is it not? So forth and so on. But the three most important, at least three most important, I'm doing quotes, is the hydroxyl radical, the nitrate radical, and ozone. All right, so if you only have a working knowledge of what's going on in the atmosphere, those are probably the big three. And the hydroxyl radical is very, 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 very important. It is extremely reactive and able to oxidize most of the chemicals found in the troposphere. Okay. It is known as the detergent of the atmosphere. That's our cleaner. Okay. Generally, concentrations are higher during the day when the sun is up and approach zero at night because there's no sunlight. And it is formed pretty much from the breakdown of ozone or the photolysis of nitrous acid, but really I'm just going to show you the ozone. So if you have ozone in the presence of light, gee, there's a lot of that in the upper atmosphere, you're going to make O2 plus an O radical. Well, that O radical can react with the water to make two hydroxy radicals. All right? And that's a good thing, but it does depend on having water in the same location. All right, only a few compounds in the troposphere don't react, or at least react very slowly or not all the way with it. And unfortunately, that's the chlorofluorocarbons. Okay, so it can't sponge or clean those out of the air. It can't get out nitrous oxide. It doesn't do anything with carbon dioxide, probably a good thing. And then methane, it doesn't play with. Those are the two components, the building blocks of ultimately carbon compounds. So it's a good thing they don't play with those. All right, this next one, the photolysis of nitrous acid. When I was doing this handout, I went down a rabbit hole. Oh, and I went down a really big rabbit hole. I never really was interested too much in radicals. So once I started looking up these real life examples for you, it just sucked me in. It's like, wow, is that why that works? So here is just a little teaser. If you are interested in any of these, maybe it's worth a read. Okay. Am I going to ask you specifics? No. Can you come up with the mechanisms for radicals like this? Absolutely. But details. Don't worry about this is for your interest only, for your, opening and broadening your knowledge. All right, what about the reactivity though of this hydroxyl radical? How does it get destroyed or removed from the atmosphere? Well, carbon monoxide will be converted to carbon dioxide, and roughly 40% of the hydroxyl radical is used up that way. Isoprene, remember that's the thing that will, ripen fruit. Isoprene, which is emitted from plants and other organic molecules, take care of about 30% of it. And methane, wait a second, you just said methane doesn't react. Okay, it doesn't react completely or very quickly, but methane is about 15%. And then ozone, other hydroperoxy radicals, hydrogen gas takes care of the other 15. All right, so that's the hydroxy radical. Well, what about ozone? Okay, ozone is our protecting group. How do you make ozone? Guess what? You take diatomic oxygen, put some high energy, and you get two oxygen radicals. If you react O2 with an oxygen radical, you get ozone. Again, highly reactive in the upper atmosphere, and we rely on that ozone for a lot of protection. And here's just a generic for chlorofluorocarbons. You can see I was going to get all deep right there and show you the whole mechanism, but let me just stop with, oh, look, this is how ozone reacts with those nitrogen compounds. Here's how it's formed, and there's what happens with the chlorofluorocarbons. And I also found this very, 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 very interesting. So the oxidant formation in the troposphere. This, hey, ozone plus NO will make NO2, but light will take it back to NO. But if you take NO in the hydroxyl radical, you can make HNO2. This was just a very nice diagram. Again, mostly for interest. Really, all I need to know is ozone and the hydroxyl radical are important in the atmosphere. Now, what we're really going to talk about in the future, though, are sugars, starches, and fiber happen to be part of the carbohydrates. Carbohydrates are polymers, and they have an acetal, or it's called a glycosidic linkage. That is coming up after we finish all of the mechanisms and the reactions in OChem 2. And then we're going to talk about the proteins. And so we talk about the carbohydrates first, then we talk about the proteins, but there's 8 main types. We have a whole chapter on proteins, and then lipids. And there's different variations of lipids as well. Now, radical reactions are really important to unsaturated lipids because the allylic location is easily reacted with. And your last one, your nucleic acid. Okay, so if we get time through the semester, we will be talking about nucleic acids. Again, went down a rabbit hole, but how do you stop, okay, these radicals? What is nature's defense against them? Okay, reactive oxygen species are ROSs. I know it sounds just like Princess Bride. What about the ROUSs? Okay, highly reactive chemicals formed from oxygen, water, and hydrogen peroxide. Okay. They are our protectors, our scavengers, the sponges, whatever you want to call it. So they inhibit oxidation. Scavenger, I guess, is a good word. They're your radical sponges. All right, because radicals are highly reactive, we don't want them just going willy-nilly doing whatever they can. And so there's a lot of naturally occurring ones. Remember, I told you quite a few lectures ago, phenol is an excellent sponge. Excellent sponge. And so you're going to see that as a repeating idea through a lot of these naturals. So vitamin C, yep, get your vitamin Cs. Okay, vitamin E, the tocopherols, they have nice phenols in them, beta carotenes and other carotenoids, some terpenoids, some flavonoids. Wow, it just keeps going and going. There are a lot of ways that nature tries to limit radical reactions. And then, okay, those are natural, but what about in our foods? What do we use that's, okay, I don't want to say artificial, but a lot of these are synthesized. Ooh, BHA, butylated hydroxyanisole. BHT, butylated hydroxytoluene. Haha, guess what that is? Phenol with CH3. Okay. EDTA, if you look at the labels on, foods, not fresh foods, but labels of things that have been canned, but they have to sit on the shelf, you will see a lot of those preservatives and antioxidants because we don't want them going bad. And I found this, and again, I was in a rabbit hole, and it was a deep rabbit hole, and it was so fascinating. But I found this, and it's talking about, hey, ascorbic acid is an oxygen scavenger, but BHA is a free radical scavenger. Seeing the difference? This one works on the O2, this one works on the radical, and they all have just a little bit special mechanisms. So this is a free radical sponge, where these work in other ways. And then really it went down a hole. Hey, for preservatives, we can have antimicrobials, but that is not into our radical realm. But I thought that was an interesting table for us. Oh, this. I wish we could make rubber in the lab, but we will be making nylon. Okay, there is what we are going to be doing. So we're going to use hexamethylene diamine, and we're going to use adipic acid, and we are going to make, do you see they just have different sizes? We're going to make some nylon in the lab. This is vulcanized rubber, like I showed you before. And last but not least, we cannot finish our chapter unless we talk about the, can you recycle it? What happens to it? So each of the numbers on your recycling stands for specific types of chemicals of polymers. So number 1 is polyethylene terephthalate. That's so hard to say. Terephthalate. Okay, these are your soft drink bottles, your fruit juice bottles, cooking oil bottles. Okay, those are the nice squishy ones. HDPE, high density polyethylene. Woo, milk jugs are much thinner, okay? Where are we going? Shampoo bottles are usually thicker. The milk jugs are made thin just so that it's less expensive. Okay. Washing, soaps, things like that. PVC has that chlorine attached to it. LDPE is the low density polyethylene. Those shopping bags, okay, wrappings, the really thin, not because they use less material, but the more flexible. Okay. Polypropylene, getting pretty heavy now. Polystyrene, whoo, packing refrigerants, things like that. And then everything else gets thrown into number 7. But I thought it would be interesting to show you what all of those numbers mean. And if you'll remember in Gen Chem, we did a lab where I had most of these, and they were in colored beads, and you separated each of the polymers out using different color, or sorry, using the density of water. So we'd add salt water until they would eventually all float, and you could collect them and separate them. All right, and here is the ultimate question. Everything I've talked about, here's what's important. Of course, you have to know the terminology, but can you do these reactions and use the correct terminology for them? And that ends our discussion on radicals. All right, until next time, jolly out.